Okay, so here's going to be an example of a free response question for implicit differentiation and related rates. To be honest with you, I think implicit differentiation is probably more likely what you're going to see in a free response question. So you'll notice I added in a little related rates part of a question, but it doesn't seem to be as much of a focus in recent years. But again, you never know what they're going to give you while you're at home. So let's take a look at letter A. So it says, write an equation for the line tangent to the curve at the point -1, 1. You're being given the curve that is y cubed minus xy equals 2. So that's an implicitly defined curve because you can't get all x on one side and all y on the other side. They actually did you a nice favor because they already gave you dy dx. So you don't actually have to do implicit differentiation just yet here. We'll talk about how you do it when you get to the second derivative. But just as like a quick reminder in case you did have to do that. And again, this is not what you necessarily need to do for this part of a question, but just to recap, let's say they didn't give you dy dx and they asked you to solve for it. You would take that y cubed minus xy equals 2. And what you would start by doing is you'd be taking the derivative, but remember during implicit differentiation you follow up every variable with d of that variable over dx or dt depending on the situation. This one would be a dx situation until we get to the related rates. So this would be something like 3y squared dy dx, because I just took the derivative of y, I followed up with dy dx. When you do negative xy, you're going to have to do product rule. So I'm going to do first, which is negative x, times the derivative of the second, which is 1 dy dx, because you just took the derivative of y, plus the second, which is y, times the derivative of the first, which is -1, followed by dx dx. And then don't forget on the right-hand side, you're taking the derivative of 2, not just 2 itself, so that comes out to be 0. You can cross out the dx dx if you'd like, and you'll notice I'm going to clean this up a little. So this is 3y squared dy dx minus x dy dx minus y equals 0. So at this point, you would get everything without dy dx to one side, everything with dy dx to the other side. So I'm going to factor out dy dx on the left, and that will leave me with 3y squared minus x. When I bring this y over to the right-hand side, this comes out to give me y on the right, and therefore I end up with dy dx equals y divided by 3y squared minus x. So you can see that's exactly what they gave you. So again, in this particular problem, if this is what you were given on the AP exam, you wouldn't have to do the work I just did. I was just doing that just so I can show you like how did they get dy dx like that and go over some of those key concepts of implicit differentiation. This is going to be a little more of like applying stuff that you can do with this original function and the derivative. In particular, I like the fact that they included one with the second derivative here. So when I'm writing the equation of a line tangent, this is still going to follow the same model as we did before. L of x equals f of a plus f prime of a times x minus a. Okay, the most complicated part of this is that f prime of a isn't going to be a function that's based on one single function value. It's actually going to be based on an x and a y coordinate. Okay, so I'm going to have something like the a value that I'm making my derivative at is -1. So f of -1 plus f prime of -1 times x plus 1, because obviously it's minus -1. Okay, f of -1 is easy. They give you that's 1. It's the f prime of -1 that's going to be the tricky part. That's dy dx at the point -1, 1. So when I plug into this function, that's y on the top, so that would be 1 over 3 times 1 squared minus -1. And when I clean that up, that comes out to be 1/4. Okay? So therefore, I'm going to have 1 plus 1/4 times x plus 1. And that would be the equation of my tangent line. Okay, part B. Find the coordinates of all points on the curve at which the tangent line to the curve at that point is vertical. So I want to find out where is the tangent vertical. Vertical tangents go straight up and down, means I have zero slope. Oh, sorry, not zero slope. Means I have no slope. So I basically have to figure out where, the denominator of my dy dx comes out to be equal to 0. So I'm going to set 3y squared minus x equal to 0. You'll notice that that's a function of x and y, so I'm going to have to do a little bit of extra work with this at a point to eventually get an actual coordinate pair x comma y where I have a vertical tangent. It can't just be some sort of a function. So if I start cleaning this up, you'll see that if I bring x to the right-hand side, this tells me that x equals 3y squared. Okay, now keep in mind that this is going to be kind of like a system of equations. When you have two unknowns, you need two equations. So I'm going to go back and I'm going to use my original function or original curve they gave me, not function. And I'm going to say, okay, any place where I had an x, I'm going to replace it with 3y squared. So I have y cubed minus 3y squared times y equals 2. As I start cleaning that up, that's y cubed minus 3y cubed equals 2, or negative 2y cubed equals 2. As I keep solving, I'll get y cubed equals negative 1, and eventually that will give me y equals negative 1. If I take it and I plug back into x equals 3y squared, I get x equals 3 times negative 1 squared, which comes out to be 3. So the place where there is a vertical tangent is the coordinate pair 3 comma negative 1. Okay, so again, vertical tangent means denominator equals 0, but again, you need to find a full coordinate pair where this happens. Okay, part C. Part C says find the second derivative at the point where on the curve where x equals negative 1 and y equals 1. So take your first derivative, so that was dy dx equals y over 3y squared minus x. Okay, I need to now take the derivative of this derivative, if you will, and remember, this is still an implicitly defined function, curve, which means that you have to follow up with dy dx, dx dx, and notice that it's a quotient, so you're going to have to do the quotient rule here. So the second derivative is going to come from bottom times the derivative of the top, which is dy dx, minus top times the derivative of the bottom. Remember, this is still implicit, so this becomes 6y dy dx minus 1 all over bottom squared, so that's 3y squared minus x whole quantity squared. Okay, so here would be my suggestion. And remember, you really don't have to do any major simplification. So as long as you plug in the right values, you can leave your answer in an unsimplified form, and I would definitely recommend that in this problem. I would maybe just start by calculating the value of dy dx. So remember, you're talking about the point negative 1 comma 1, so your y value is 1 over 3 times 1 squared minus negative 1. Or 1/4. Oh, I probably shouldn't have done that again because you already just did that in part A. And now I'm going to plug in the other values that I have. This is going to go in place of any place that I have dy dx. So I'm doing 3 times 1 squared minus negative 1, watch your parentheses, times dy dx, which was 1/4, minus y, which is 1, times 6 times y, times 1/4, minus 1, all over 3 times 1 squared minus negative 1 whole quantity squared. And honestly, I would leave my answer just like this. As long as you know you plugged in the right values and you didn't forget anything, there is literally no reason for you to simplify and risk making a mistake. That is a perfectly acceptable answer. If you did go further and simplify just for your own benefit, this does come out to be 1 over 32. Okay, last question, and I know this changes gears because, you know what, let me go back and copy this really quickly. Okay. I know that this changes gears because this is going to a related rates question, but I just wanted to kind of show you again an example of doing related rates just in case. But like I said, if it's going to come up, I don't think it's going to be just a related rates problem. I think it would be incorporated into a related rates problem, and especially this year because they're merging so much stuff together, I can see like each component of some question is going to involve some part of stuff that we worked with. So it says, find how fast the surface area of a sphere is changing when the air is being pumped in at 16 pi inches cubed per second at the moment when the radius is 4 inches. So remember that you need when you're doing related rates, it's technically implicit differentiation, but with more of an application. So you need a formula that you're going to be able to do implicit differentiation to. So if I think of a volume formula for a sphere, 4/3 pi r cubed, and the surface area formula for a sphere, 4 pi r squared. What are we trying to find out here? We're trying to find out how fast the surface area is changing. So let's take the derivative of that surface area formula. You're taking the derivative as in terms of t. So remember, every variable gets followed up with d of that variable over dt. So that's why I start with dsa dt. This becomes 8 pi and then r dr dt. Okay, so now if you take a look at the information provided, I'm looking to calculate dsa dt. I know the radius is 4, but I don't have anything yet for dr dt. So I'm going to have to use the fact that they're pumping volume, the volume of the air being pumped in is 16 pi inches cubed per second. Now, inches cubed per second is a rate of change of the volume. So let's take the derivative of the volume, similar to what we did before. So this comes out to be 4 pi r squared dr dt. I know that this is 16 pi for dv dt equals 4 pi. My r is 4 squared dr dt. If I divide both sides by, 48 pi? Oh no, sorry, 64 pi. Okay, so 64 pi. Okay, I can clean this up, and then I can see that this comes out to be 1/4 is dr dt. Okay, so again, you could actually even left it as 16 pi over 64 pi. You don't have to simplify it. I just thought it might be a little bit easier that way. So now I'm going to go plug in. dsa dt is what I'm looking for. 8 pi, I want the radius to be 4. My dr dt is 1/4. Okay, so as I start simplifying, dsa dt comes out to be 8 pi, because those 4's cancel out. So the answer would be 8 pi inches squared per second. And that's how fast the surface area is changing at